Okay, so chapter 11, part 2. It's a little bit of a rehash here, talking about virulence and virulence factors. If you remember, we brought these up in chapter 3, um, specifically saying that structures we were listing were going to be considered virulence factors because they helped fulfill the 5 requirements. Uh, Now, when we talk about virulence, it's the organism's ability to establish itself in a host, which will include what we term establishment or attachment and defeating the host defense, and the ability to cause damage. A virulence factor will be any characteristic or structure. This will include things like proteins, enzymes, secretions, okay, that contribute to the organism's ability to, again, fulfill those 5 requirements of infection, establishing itself and doing things like causing damage. Okay. So, here it is again, a rehash of the 5 requirements of infection: entry or getting in, establishment or staying in, usually this involves some type of attachment, defeating the host's defenses, damaging the host, and being transmissible. So we're going to take these one by one. We'll start off by talking about that first step, entry. Okay. And what we call portals of entry. Now, a portal of entry is any route that the organism takes to enter the body. One of the best examples of these, and what you'll see a lot of when it comes to the portals of entry, are that these are very often associated with openings within the body. So it's pretty much exposure to the outside. Ear, eyes, nose, mouth, vagina, anus, urethra, okay, all going to be considered portals of entry. We'll also see breaks in the skin as a portal of entry. This is specifically called the parenteral route. Okay. And this also allows us to begin identifying organisms as coming from an exogenous source or coming from an endogenous source, or being an endogenous or exogenous infection. Exogenous organisms, what you're saying is that the microorganism originated from outside of the body. Okay, it's something you picked up by touching another person or another object. You breathe something in. Okay, it's coming from the outside. It's basically contact. Okay? Meanwhile, an endogenous infection is usually when we move a microorganism from one area of the body to another. Okay, so what we see as normal flora in one area actually gets moved to an area where that particular organism is not okay, and causes an infection. Now, a good example of this is people using the restroom, not washing their hands, and actually moving bacteria that you would normally find in the intestinal tract into their eye or into their mouth. It's something we call fecal oral route. Okay, so just because that bacteria is okay within the intestinal tract doesn't mean it's okay within the eye. We see a lot of bacterial conjunctivitis actually being brought on because of that. Now, most pathogens have actually adapted themselves to a very specific portal of entry. What that means is that if they come in the wrong portal, there is no infection. So, in other words, think in terms of if you have to breathe it in and it lands on the skin of your foot, are you going to get sick? The answer most of the times is no. Okay, especially if we consider that you have to breathe it in, it has to come in through the respiratory tract. You're not going to get sick. It's the wrong portal of entry. An example of this, the nasal mucosa with the influenza virus, okay, uh, will cause an infection. So the result there is actually infection. But if the virus makes contact with the skin, you get no infection. So touching influenza virus isn't what's going to make you sick. It's going to be touching it and then rubbing your nose or breathing it in after somebody coughs it. It's got to come in through the nasal mucosa. Now, there are a few organisms out there that can enter through more than one portal of entry. Okay? Mycobacterium is a good example of this. It can actually enter through the respiratory tract, which is what we commonly think of when we start thinking about TB. But there is a gastrointestinal version of tuberculosis. Okay? Actually, symptoms are very similar to what we see in the lungs. Lots of excessive inflammation and mucus production. Okay? Uh, Organisms like Streptococcus and Staphylococcus actually enter through the skin, the urogenital tract, the respiratory tract. Interestingly enough, where these enter the body actually determines what type of infection you will be dealing with. Okay? So these are organisms that, depending upon where they come into the body, can cause a wide variety of different types of infections. Now, one thing we also note that it's not just where the organisms enter, it's also how many organisms enter. Your book is calling this the size of the inoculum. Realistically, lots of times epidemiologists will refer to this as infectious dose. Okay? And an infectious dose is the minimum number of microorganisms you have to come in contact with through that correct portal of entry that can cause an infection to happen. Okay? Now, lots of times you'll see this termed an infectious dose 50 or ID 50. What this means is that it's the infectious dose for 50% of the population. Okay. It's also not unheard of to hear LD 50 thrown around. This is a lethal dose. Okay. Again, for 50% of the population. And by lethal, we of course mean that this dose will kill. Okay. So what we see is that microorganisms with smaller ID and LD numbers actually have a greater virulence because it takes fewer organisms to make an individual sick. Okay? So they're much more likely to stay in, grab on, and cause damage. A couple of examples here. The infectious dose for rickettsias, think Rocky Mountain spotted fever, is a single cell. The ID for tuberculosis, giardiasis, coccidiomycosis, about 10 cells. Gonorrhea, it's 1,000. Typhoid, it's about 10,000. For cholera, it's about 1 billion. Okay? Now, reality is that's infectious dose. Do not get this confused with likelihood that you get disease. To come in contact with a rickettsia that causes Rocky Mountain spotted fever, you actually have to be in an area where they have certain types of ticks. Okay? You have to be bitten by the tick. The tick has to have the rickettsia, and the rickettsial organism has to have enough time to make its way from the tick into your bloodstream. Okay? So even though it's a single cell, there are a lot of factors that go into frequency of actually contracting the disease. Meanwhile, if you're in an area where there is a cholera outbreak or cholera is endemic, meaning that it's pretty consistently there, cholera is going to be found in the water. 1 billion cells in a glass of water is very, very easily done. And lots of places where we do see cholera actually have limited access to sanitized water. Okay? Everyone is utilizing the same water source. When it becomes contaminated, cholera spreads rampant. Okay? So step 2, okay? Attaching to the host. Now, we also term this adhesion. Okay? If you remember, I called step 2 establishment all by itself. Your book is blending a lot of these together. Okay? Here what we're seeing happen is these organisms are gaining a foothold on the host. Okay? In other words, they're grabbing on and not letting go. Okay? Now, this depends upon specific binding between molecules on both the host and the pathogen for the most part. So what we see is a lot of individual receptor cells, okay, that you would find on the outside of a host cell, very specifically docking with the microorganisms. Okay, ligand, these are, anytime you see ligand or lig, it means to tie. So ligands are basically binding or bonding molecules. Okay, so the ligands attached to the receptors. This actually allows the microorganism to grab onto the host cell. Okay, now pathogens are limited to cells to which they can bind. Okay. So what that means is that if the pathogen does not have a ligand, it doesn't have its own sort of docking site for liver cells, then that pathogen isn't going to attach to liver cells. Or if it doesn't have a docking site for human cells, it only has a docking site for cattle, okay, then it's only going to attach to cows' cells and not attach to us. It's one of the reasons why certain diseases don't affect certain types of organisms. Okay. Now, firmly attaching to a tissue or a cell is always a prerequisite for causing disease. Okay? Because our body is full of mechanisms that their entire job is to actually flush out the microorganisms. So they've got to have a way to grab on and hold on. Okay? So these adhesion mechanisms become very important. Okay? Now, a couple of other examples aside from that ligand binding. Okay? Uh, these are specifically virulence factors. Look for these when you're doing the 5 requirements of infection report. Okay, fimbriae or pili, which we call those attachment pili. If you remember, I said they were like Velcro on the surfaces of the cells. Okay, the surface proteins. We're talking about the ligands here. Right. Adhesive slimes or capsules. So slime layers and capsules, because they have that sticky sugar consistency to them, are very often sticky. Okay. Viruses, often attached by specialized receptors. It's what gives viruses the majority of their specificity. If you remember, when we talked about parasitic worms, we talked about the suckers and the hooks that you can find in these scolexes. And this will include things like barbs. They're basically attaching and grabbing on to individualized tissues. And if you remember the helminths, that was usually the intestinal tract where they grabbed on and then proceeded to utilize nutrients from their hosts. Now, microorganisms that do not establish themselves as normal biota, so that don't become part of your normal microflora, are going to encounter immune defenses. Okay? The most specific immune defense, and that one that we know the majority of microorganisms are going to come in contact with, is phagocytosis. No matter what, anything that has to do with phagocytosis, the phagocytes are an immune system response. Okay? So defeating phagocytosis means that you're defeating an immune system response. Okay? Now, we actually give a name to the virulence factors that are specific to defeating phagocytes. We call them anti-phagocytic factors. Okay? And some examples of this include things like leukocidins. Okay? Leukocidins, leuco for white, cidin like cidol. Okay? These are chemicals that very specifically kill white blood cells. So leukocidins are going to outright kill phagocytic cells. Streptococcus and staphylococcus bacteria have massive amounts of leukocidins. They're actually very good at killing blood cells, even red blood cells in some instances. Slime layers and capsules make it difficult for the phagocyte to engulf the pathogen. So they sort of slip out. If you remember, I said these have that slimy consistency. They sort of slip out, okay, from within the phagocyte as it tries to wrap its way around the pathogen. Some bacteria will actually survive in the phagocyte. They don't mind being phagocytized, but they will not be digested once in the phagocyte. Okay, so you can see it here. Okay, capsule around the bacterium. Okay, encapsulated bacteria basically slip out from within the phagocyte. Okay, or we can see, well, when they live within the phagocytic cell, we often term that incomplete phagocytosis, because they did the ingestion part, but the digestion is lacking. Okay? There are a lot of ways to do this. One of the most common ones is to prevent the fusion of the phagosome, which is the little vesicle that the bacterium will be in, and the lysosome, which is the vesicle that holds all the digestive enzymes. If you prevent fusion of the phagosome and the lysosome, basically the digestive juices never get to the bacteria, so bacteria often will reproduce inside of a phagosome if it's unable to connect itself to a lysosome. Okay. Now, the fourth step, causing disease. Okay. Here we're talking about tissue damage very specifically, and there are 3 main ways that microorganisms cause damage to the host. Now remember, for the most part, this is not something directly done by the microorganism. Their goal is not damage the host. Their goal is survive and reproduce. Damage is a consequence of that. Okay, so 2 types of direct damage. In other words, the microorganism is responsible. Okay, Direct damage to the action of enzymes and direct damage to the action of toxins. This will include both endotoxins and exotoxins, so we're going to revisit endotoxins. Okay. And indirect damage, meaning that the damage itself is not caused by the microorganism. In indirect damage, we see the host defense responding excessively, okay, or in some instances inappropriately. In other words, we see excessive amounts of inflammation, excessive amounts of reaction to the organism, and what does the most damage is that excessive response from the body, okay, your immune system overdoing it, and it's not really something that's caused by the microorganism itself. So, we'll do direct damage by enzymes first. We're talking about extracellular enzymes, or what we term exoenzymes. In other words, these are made within the cell but secreted out of the cell. Okay? Now, very often exoenzymes are meant to dissolve. Okay? Specifically, what they're going to dissolve are host tissues. Okay? Things like defensive barriers that prevent the organisms from spreading. Remember, these guys would like to eat, multiply, and spread throughout the body. That's their goal. So a lot of the enzymes that are secreted by microorganisms are meant to break through barriers to help the disease spread. Okay? Examples of this: mucinase, digesting through mucous membranes. Okay? Hyaluronidase, and if you don't know, hyaluronic acid, okay, is what grounds animal cells together. It's the substance that actually puts animal cells together with one another. So it would be what you found here. Okay. Hyaluronidase will actually digest its way through the hyaluronic acid, okay, allowing for microorganisms to spread between cells. In other words, invading deeper layers of tissues. Okay. We actually see one that's not mentioned above, collagenase here, digesting through this collagen layer so that we can actually move microorganisms deeper into tissues. Coagulases and kinases. Interestingly enough, you'll see coagulases clotting around bacteria, and you would think this would be bad for the bacteria. What happens is we see this clot formation. The issue is that the clot can move around. Okay? And when the clot moves to a suitable area, kinases are released, dissolving the clot away and allowing the organisms to basically settle down in a newly discovered area. Okay? So coagulases are clotting enzymes while the kinases digest clots. They're being used together. I always think of this like a little Trojan horse of bacteria. Okay. You move it in, break it apart, and all the damaging organisms get released to a nearby tissue. Now, when it comes to the toxins, a toxin is a chemical product of microorganisms, plants, even some animals that produce toxins. The big gist here is that toxins are poisonous to other organisms. Okay? They come in two varieties, endotoxins and exotoxins. The endotoxins we have talked about before. If you remember, our example of this is lipid A. And we only find this in the cell, the outer membrane, part of the cell wall of gram-negative bacteria. Now, exotoxins, unlike endotoxins, are actually produced within the bacteria and excreted. Okay, so these are going to be released by the organisms. Toxins get named and characterized according to their target system. We see neurotoxins targeting the nervous system, enterotoxins targeting the GI tract, hemotoxins specifically targeting red blood cells, and nephrotoxin targeting places like the kidneys. Now, there are other varieties of this. These are just the ones that I am mentioning. Okay. So, again, the exotoxins, we're going to be a little bit more specific here. Okay. These are proteins that are excreted by the cell again. They have a strong specificity for a target cell. Okay. And they have extremely powerful effects upon the cell. Sometimes they can even be deadly. Most commonly, exotoxins affect cells by damaging the cell membrane and lysing the cells or beginning lysing of the cells. Okay. Some of them actually go beyond disrupting the membrane and make their way into the cells, to the internal cellular structures, and disrupt intracellular function. So they'll stop things like enzymatic pathways. Now, an example of this are what we call hemolysins. Okay. Uh, Hemolysins specifically disrupt the cell membrane of red blood cells. Okay. What they do is cause the release of hemoglobin from the red blood cells, and this basically destroys the functionality of the blood cells themselves. Okay. Very commonly, you see these produced by Streptococcus pyogenes, okay, which produce things like streptolysins. Staphylococcus aureus, though we see the Streptococcus and the Staphylococcus are very good at this, will often produce two types of hemolysins called alpha hemolysins and beta hemolysins that vary in their degree of destruction of the red blood cells. Okay. The alpha hemolysins actually usually just release the hemoglobin, while the beta hemolysins seem to do a little bit better and are a little bit more destructive when it comes to the red blood cells. So you can see this is a blood agar plate that we're looking at here. Okay. And the redness of the plate comes from the fact that it's impregnated with blood. The beta hemolysins seem to be digesting through large amounts of the blood, and that's why you get the clearing of the plate. Now again, the endotoxins, it's that lipopolysaccharide layer. If you want to talk about effects themselves, endotoxins, toxic more so in higher amounts. We see fever, inflammation. The exotoxins are very specific to a cell type. Okay. The endotoxins pretty much work everywhere. It's a generalized systemic poisoning. Okay. Again, this is going to be dose dependent. It depends upon how much endotoxin one is exposed to. High doses are going to be very dangerous. Low doses, probably not so much. Okay. Okay. So a little bit more of that lipopolysaccharide layer. Again, outermost layer of the outer membrane of gram-negative bacteria. So if you remember the gram-negatives, we had cell membrane. We had the peptidoglycan layer, so cell membrane, peptidoglycan layer, it was very thin, 20%, okay? And then we got that additional outer membrane for the lipopolysaccharide layer, okay? This is where your lipid A can be found, okay? Again, anchors the LPS part of the outer membrane layer. Excessive amounts of lipid A will induce fever, inflammation, possibly hemorrhage. Diarrhea is a very common side effect. Mostly we see this being particularly dangerous in blood infections of Salmonella, Shigella, okay, Neisseria meningitis, okay, and Escherichia coli. Okay. The meningitis, okay, we often see in the central nervous system. Okay. Meningitis being the end result there, but it will show up in the blood sometimes. Again, this is our one example, the only one of an endotoxin. Okay. Put them together, gram-negative endotoxin. Okay. The gram-positives can have exotoxins, but only the gram-negatives have an endotoxin. Okay. So, I am particularly fond of this image. Right? It sort of breaks it down for you. We see enzymes in action as our first mechanism of direct damage. Again, digesting their way through tissues, because that is usually the goal here. Toxins is another means of direct damage. Exotoxins being produced in the cell and expressed out of the cell. Okay. The endotoxins as part of this lovely red gram-negative cell wall. That as the cell wall is being broken down, the cell is dying, they get released out into tissues. Okay. And then the indirect damage. Okay. Host defenses over-responding, too much inflammation in an area that is not very good with inflammation, like the lungs or the brain. Okay. It's an overreaction of the immune system. It's an inappropriate immune response. So I am going to stop here, and we'll talk about transmission in the next section.